Hi, everyone. Welcome to the GRASP SFI seminar, where today we'll be listening to a talk by Laura Hallock. Hallock is a PhD student from UC Berkeley, where she works in the Heart Lab under Dr. Bashi. Her research focuses on developing musculoskeletal dynamic models for applications in exoskeletons, prostheses, and physical human-robot interaction. Before starting her PhD, she worked on neuromuscular modeling for lower limb prostheses in the MIT Media Lab's biomechatronics group, and on perception software for Carnegie Mellon's humanoid robot Chimp. Today, we're really excited to hear her talk to us about her recent work in sensing and modeling neuromuscular dynamics. So please welcome Laura Hallock. And as a reminder, please feel free to put your questions in the Q&A throughout the talk.
Awesome. Thanks for the great introduction, Rebecca. As she mentioned, my name is Laura Hallock, and I am a PhD student of Rujna Baichi in the Human Assistive Robotic Technologies Lab at Berkeley. And today I'm going to talk about something that might be a little bit left field for the GRASP lab, in particular my work on musculoskeletal modeling, and in particular inferring muscle forces for eventual integration into these systems. And I just want to start with a little bit of motivation of why we actually care about measuring muscle force, which isn't necessarily obvious to a robotics audience. But fundamentally, muscles are the actuators of the human body, and we really, because we don't really fully understand the way that they behave and the way that they work, our understanding of the actual capabilities of dexterous human motion. You see an extreme example here of someone doing contact juggling. We really don't fully understand how people do that, let alone mimicking these behaviors in a device. Robots certainly can't do that yet. And in particular, I want to highlight a couple of applications that I'm really working towards with the work that you'll see today. So first, building safe and expressive assistive devices. So to unpack that a little bit, we have all these cool prosthetics. In particular, I want to talk about hand prosthetics that have they're anthropomorphic. They have all the right joints in all the right places, and they all sort of do this. They all, have one-ish degree of freedom in terms of the control that's conferred on the user. And so those devices just aren't that expressive, aren't that capable yet, because we don't know how to control them. And secondly, as we start to strap these devices to people, and we really need to understand how those devices are then influencing both human behavior and the safety of those behaviors. So if I strap an exoskeleton on and that causes some, damaging muscle reaction, then that's not a safe device. And we really are sort of the dark secret of musculoskeletal modeling these days is that we really don't have a way of evaluating this kind of safety or evaluating what muscles are even doing, what the system is doing. And lastly, just, so we really don't know how to modify this, safely and expressively, this kind of behavior. And thirdly, as we start to want to, port these kinds of behaviors to autonomous robots or to teleoperated robots, that's also a challenge. We're kind of restricted to big, bulky devices in which we're moving them kinematically, but in terms of understanding even just the simplest possible case of mimicking a human's force and impedance trajectory on a robot is completely beyond our capabilities right now because we can't measure that human system. So, that said, there are, the mechanism by which muscles are, by which human motion occurs, by which muscles exert forces is known. Basically we have our brain, our neurological system sends an electrical signal to the muscle. That causes this ratcheting of fibers together called the cross-bridge cycle, which causes the muscle to ratchet together and pull the tendon, and that imparts force to the skeleton. So at a high level, we do understand this mechanism. But and in general, for people who are trying to infer these musculoskeletal dynamics, they use basically some sort of measure of this neurological activation, usually using a tool called surface electromyography. It's an electrode that goes on your skin. Then they feed it into some sort of modeling software that generates, the predicted muscle forces, and that gives you your muscle force. But unfortunately, these are really pretty limited frameworks, even though they've opened up a lot of avenues, especially in lower limb dynamics modeling. You can't customize them very much based on the individual person, and a lot of the assumptions that underlie these models are really unverified. So a lot of them will say, okay, humans are just minimizing the amount of energy, and that's how we know what all of the forces are doing. But we don't really know if that's true, and in fact, in many cases, that's not true, since we will, exert additional force to maintain smooth motion. So the insight that I'm leveraging in my research is actually kind of bypassing this model of complex neuromuscular contraction dynamics, and instead trying to measure these dynamics closer to the source. In particular, during this muscle motion, that causes a deformation signal, which we can actually look at via ultrasound. And so my research focuses on taking those deformation signals and using those to infer output force. So the core hypothesis basically underlying this work is that this kind of individual muscle force, since we can look at individual deformation, can be inferred from that deformation, and we can detect it via ultrasound. And this can be measured and quantified because of this underlying physiological mechanism in which there's necessarily a change in shape of the muscle, which causes a change in tendon length, which causes this output force. So fundamentally, what the goal of my research is to measure these individual muscle forces via ultrasound based on these shape changes. And this is basically a system identification problem. We want to build these better models in order to extract potentially more control signals, and just to better understand these musculoskeletal dynamics. So this is a model development and validation problem. And that's kind of the core of this research. At the same time, this is a really understudied problem. And in fact, almost no one has looked at this relationship between deformation and force. This is a completely new field. So I've actually spent substantial time and effort on just doing some preliminary exploratory analysis of this phenomenon, and generating data so that we can study it in a systematic way. So I'll present both of those sets of work today. The center one model development is currently being undertaken. And lastly, I'll also present a few proof of concept applications in how I see this research moving forward. And I'll close with some alternate sensors that we're looking at, and conclude. I do want to mention that this talk is kind of set up in 3 pieces. So if I will pause at the end of each set just to take questions from that section. So go ahead and feed your questions into the Q&A, and we'll have periodic chances to look at those. Okay, great. So with that, I'll move on to this initial exploratory analysis phase of the research. So I mentioned before that we have this nice physiological model for what is happening when muscles deform and force is exerted. Muscles are roughly isovolumetric, so they'll stay the same volume roughly throughout a contraction. So that means that as this, if there is this ratcheting motion and the tendon's getting longer, then necessarily you're also going to see deformation in the other dimensions. But in practice, this is actually we're not a two-dimensional entity. We are an incredibly complex set of squishy tissues. There's a whole boatload of contact dynamics that actually dominate the signal, even more so than this nice, muscles get bigger in the center as the force increases. That's not even necessarily true, depending on where you measure. There's also, it's occurring, any individual muscle force is occurring in this context of many, many other muscles, each of which is exerting forces of their own. So there's a huge amount of geometric complexity. And in addition to that, there's tons and tons of variation across people. It's really difficult to make any sort of generalization across even a healthy population, let alone the kinds of populations that would be most helped by this kind of technology, like individuals with muscular dystrophy or who have had, say, a spinal cord injury or Parkinson's disease. So there's all sorts of additional complexity built into this. So we had to start with a very simple initial question of, can we actually correlate any sort of simple muscle deformation signal with this output force? Because actually before this research that wasn't known. So as kind of a starting point, we took we kind of threw the book of sensors at the problem a little bit, but we collected while a subject basically pressed upward, you'll see the force trajectory and kind of a bunch of different force pulses, both pulsed and sustained. We had them press upward using just elbow force. And while they were sensorized with basically an ultrasound and with some EMG electrodes here. And so from this ultrasound scan, which was of the brachioradialis muscle, which is one of the elbow flexors, we collected so from this individual contour of that muscle, we collected 3 representative signals: cross-sectional area over time, thickness of that muscle, and something we defined as aspect ratio, so that ratio of the thickness over the perpendicular width. And in addition to that, as I mentioned, we collected a couple of those electromyography signals that I discussed before, so a measure of how much the neurological system is activating those muscles. And so for an additional data set, we placed the subject's arm at 5 different elbow angles. And so meaning that the force was measured from this from a load cell on this handle. But the robot's job was just to hold that load cell. It was completely static, and these are what's called isometric contractions. So the human was not actually changing kinematic configuration. But we tested at 5 different kinematic configurations, and then we tested at a representative configuration 4 more subjects, several of these force trajectories. So looking at, and then we explored the data, basically, because we had, as I said, no one had even done any kind of correlation analysis on this. So even looking just at a couple of representative cross sections of the muscle at a no force versus a high force condition, you can see that we're roughly starting to see that as the cross section gets bigger, the force does increase, but that's not the whole story. The contact dynamics are really evident here. Things are squishy and not necessarily easy to parse. But for any given angle, there is a consistent just Pearson correlation with that output force. So if you look at this plot of just plotting flexion angle versus this correlation coefficient, you can see that for most angles up to about 82 degrees, these cross-sectional area values are well correlated with that output force. Now this drops off a little bit towards very high flexion values. So when your arm is close to as fully flexed as possible, and that could be for a number of reasons that we're still exploring. So some of it could be the muscle belly kind of moved completely out of the frame of your ultrasound, and so maybe you're just not seeing a piece of it that's representative, or maybe these signals just aren't as correlated at those angles. And in particular, one other interesting thing is that if you looked at this activation measure, that activation measure actually ends up more correlated with that output higher angles. And so this is just a single subject. These are, maybe this does indicate that some sort of hybrid force inference approach where at higher flexion angles, where activation is really a better measure of this. Or maybe this is something specific to that individual. So similarly, if we look at this kind of data across subjects, so looking at these 5 different subjects, this no force and high force condition, we see even more variation. So the morphology of how those muscles move is completely different depending on the individual. But that said, there was for each of these individuals a strong correlation between these. So you're looking at the absolute value of the correlation, a strong correlation between all of these measures, so cross-sectional area, thickness, and aspect ratio for all of the subjects. They were all correlated. But interestingly, if we look at the fifth subject here, that correlation was still quite strong between cross-sectional area and force, but it was actually negative, meaning that cross-sectional area very reliably decreased with force exertion. So that could be just something specific to that individual. That individual was significantly older than the other subjects, so it might be some property of aging musculature, but this is definitely worth sort of exploring more in depth. But it kind of highlights this importance of looking at different subjects and evaluating very precisely what signals we're looking at for this kind of force inference problem. So in particular, this was kind of a a very preliminary set of analyses that just show, basically, yes, we can see, even in these very simple signals, we can start to see, this is a promising way of potentially doing this kind of force inference. But there's a couple of challenges that we're going to have to tackle before we expand this research further. So first, one of the major challenges with doing any kind of research like this is this annotation problem, where, as I showed you these nice time series plots of this cross-sectional area and thickness, but in order to extract those, we actually had to go through thousands and thousands of these cross-sections and annotate manually that cross-section, which is, subject to human error and also just prohibitively time intensive. And, it also means if we're having to do this annotation ourselves, that we can't immediately use this, this cross-sectional area value as a control signal. So, that's a problem we'll have to tackle. And second, even though we saw, based on, this one particular cross-section of the muscle, we saw some promising signals, it's still not clear exact measures or thickness measures relate back to that force. And depending on, so this is just a quick study of looking at 3 different places along the forearm, looking at the same brachioradialis muscle. Depending on where you look, you might see this nice, those measures increase with force production, but you might see something completely different. And so there's really, they're complex signals. So today I'm going to talk about some ways that we addressed kind of both of these. So to address this manual annotation problem, we are working on a system to track these contours over time using optical flow. And we've actually got I've got a talk on that coming up at BioRab 2020 at the end of this month. And so I'm not going to talk too much about that today, but know that that is something that we are working on, is tracking these contours in real time so that we can start to extract those signals as control signals. But what I want to focus on today is the second problem of, it's still not clear what we should even look at in terms of this modeling. And so I've done a lot of work on, okay, if a single cross-section isn't telling us what we need to know, what we really want to do is we want to observe the whole muscle. And we want to do it under, multiple joint positions, in this case, multiple elbow angles, since, that's, as we saw before, that really affects what you're seeing. And also under these multiple loading conditions, since ultimately what we want to be inferring is this force value, not the kinematics. Okay. So in order to do that, we built this system to actually start to observe these muscles in 3 dimensions. So you could do this with something like an MRI, but that's very slow and somewhat limited in terms of your range of motion. And so we adapted an existing system called the Plus Toolkit to basically use motion capture to track an ultrasound probe as we did a full scan of the arm. And in this case, we focused on the biceps, another elbow flexor, since it's a little bit bigger. We had focused on the brachioradialis before because it fit more in frame, but in this case, we're looking at multiple frames anyway. But basically the way the system worked is, we took this full ultrasound scan of someone based on the motion capture tracking of that probe. We could then or we could then generate these 3-dimensional scans, and then we performed annotation of those scans for the biceps and the surrounding tissue structures. And note that, this time, instead of doing a series of force pulses, because we need them to stay still, we're really restricted to statics. And so once we, have some insights from these 3-dimensional data sets, then we hope to be able to port those over and take a more targeted look at the dynamics. So for, an additional data, or for an initial data set, we collected, as I said, data from the elbow flexors, in particular the biceps, from 3 different subjects. And we took this full arm volumetric scan under 4 different elbow flexion angles, from sort of fully extended to about 90 degrees. And we did that under 5 loading conditions. So fully supported by an experimental jig, so not exerting any force at all. Just performing gravity compensation, and adding various levels of weight to the wrist. So that gave us kind of a nice spread of different weight values, or different load values. So based on this data set, here is one piece of that data set that was collected. So looking at 3 different loading conditions, fully supported, so no force at all, through this high force condition, and at 3 different representative angles. You can already just qualitatively see some of the things that I've been talking about. So if you look at, for example, the same angle for 3 different force values, you can see that muscle starting to bunch in the middle and get fatter, so that tendon can lengthen and exert force. And similarly, you can start to see some of the possible sources of the different kinematic values that we were seeing before. So looking at so kind of seeing the muscle slide up the arm as the arm flexes. So this data set in itself was very much the first of its kind. And so one of the first things we did upon generating it was actually put it online for others to use as part of the SimTK database, which is full of a lot of musculoskeletal modeling frameworks. So if anyone in the audience is interested, we're happy to share this data. In fact, it's already online. It's useful not just for some of the inference problems I've been talking about, but also for people like the animation community who are maybe more interested in making characters behave in a certain way and look natural. So that's sort of a contribution of itself that I wanted to highlight. But in particular, this is very much a preliminary data set, and so there were a couple of things we wanted to modify before really digging heavily into this data. So first, we only took this data from 3 or 4 subjects, and the way in which we actually imposed the force conditions wasn't particularly representative. So we had initially just attached weights at the wrist to sort of avoid any confounding wrist flexion, but that meant that as the arm came up to 90 degrees and the weight was pointed straight down, that meant that the loaded 90-degree condition wasn't actually that different from the unloaded condition. And so to address that, we actually modified our experimental protocol slightly and took a new data set with 11 subjects, where the protocol was very similar to the previous one, but we, instead of having just weight attached to their arm, we actually had them press upward on a load cell, again attached to a robot, purely to place it in different places in space, and had some visual force feedback, so that the person could maintain a particular specified force and sort of trace the trajectory over time. And it turns out humans are pretty good at that. It was challenging for some of the higher levels of force, but certainly for the 10%, 30% of maximum values that we used, it was calibrated per subject. People were very good at maintaining that force over time. That addressed one piece, and that actually became a second data set that's been released online. But I want to highlight again, one of the major challenges here was, again, this annotation problem, where annotating these tissue structures manually took probably hundreds of hours, if not thousands of hours, and thousands of slices. So one of my undergraduate's projects has been to automate that process of data annotation. And we tried some sort of classical registration methods, but ultimately we've landed on, I believe, like most people, on a deep learning based method, using a UNet to look at each slice and segment out. In this scan, we focused on the biceps and the humerus in order to sort of align that scan. And so this UNet was able to, in particular for the region of the muscle that we're most interested in looking at, so sort of the belly part of it, was pretty good at doing that segmentation. So I can kind of toggle between a representative scan of that neural network based segmentation. So this was super helpful and has actually started to allow us to really do more deep analysis on this data set. And as I said, this has now become the OpenArm 2.0 version of this data set, which is online, along with all of this automated annotation code, all at that same repository. All right, so that's kind of all I wanted to present in terms of generating all of this initial data. So I'll pause for a second here and take any questions just related to that first section. Or if there are no questions yet, Rebecca, you can just let me know and I'll move on.
Yeah, we have no questions from the Q&A yet. Just making sure you guys know that's there, but why you move on, and then we can take questions at the end.
Okay, great. Okay, so sort of everything I've talked about so far was basically in service of, some of it was kind of an end in itself, but was very much in the surface of this problem of, muscle force inference. And so, the next step in this process is really diving down deep and figuring out what the best models are to represent the deformation force relationship that we're seeing. So I just want to back up a little bit. And, I've mentioned before this nice, sort of ellipsoidal model of the muscle expanding. And so looking at some of this 3D data, we started just by saying, how close is what we observed to this simplified model that we saw before. So to do that, this is actually looking at that first data set you saw, so the initial 1.0 data set. But we looked not just at a single cross section, but at cross sections at each sort of X value along the humerus of each cross section of the biceps. And in this case, we looked at both cross sectional area and thickness. So looking at each cross sectional area value, as elbow flexion increases, you can start to see the muscle sort of squish together, and that's reflected in these sort of quadratic fits to these cross-sectional area values. You can see that it's a little small, but for example, at 90 degrees, that quadratic is taller and fatter in the middle, whereas it's more longer and more extended for the 30-degree one. Thickness was a little bit messy, and so I won't talk too much about that with respect to these 3D scans. I think depending on, because the muscle sort of wraps around in different ways along the humerus, it's not clear that the thickness value that we think we're measuring is consistent across the scan. But so that's sort of the kinematic relationship that we saw, which was sort of nice preliminary validation that the signals we're seeing are sort of representative. But in particular, what we really want out of this is not some, kinematic inference. We can measure kinematics using motion capture, using goniometers. What we really want is this measure of force. And so looking for each particular angle at the delta between the cross-sectional area before and after that force output is a little more enlightening. And so for each, between like the low force and the high force conditions, we can see that there is a sort of reliable location at which you do see that as force increases, the cross-sectional area gets bigger. So even though the muscle has changed locations, there is that area of maximum cross-sectional area change. Then, this is kind of a nice, cute, low-hanging fruit result for, okay, if I wanted to infer force right now, then maybe that's a good place to put a cross-sectional area sensor. And interestingly, that's not actually the location of the maximum cross-section. So if you look at the actual, muscle, fattest part of the muscle belly, that's not where you see this, which is a little unexpected and possibly related to, the contact dynamics. But this starts to show us how, okay, for, let's say I have a system in which I know the kinematic configuration, and I know this deformation value, can I start to infer force? Okay, so taking this a little bit farther, this still is not necessary. These cross-sectional area values and things like that are still very sort of gross values for what we're seeing. And there's a lot more nuance to how that deformation happens. And so one other piece that we're looking at is something called statistical shape modeling. Which is essentially principal component analysis for shapes. So you can parameterize a given contour of that cross-sectional value, or the contour of the cross-section as just a set of points, and then look at how that set of points changes over time, or changes based on force value, and evaluate what sort of the principal component shape change is for each of those different conditions. And you can start to see the difference between kinematic changes and force-associated changes. So if you look at, for example, there are cases in which there was no force, but we just varied the angle, the elbow angle, then you can see that the principal shape change as measured by this variance over here is basically that the muscle kind of slides off to the side. Whereas if you're exerting, keep the angle the same and keep exerting force, then you can see the muscle kind of pop up off to the side. And based on this chart, these are pretty low dimensional signals. You only need 3 or 4 components to represent most of the variance. So this also looks like a promising direction to actually extract signals. Okay, so now I'm going to back up a little bit again. We've seen some evidence that we're on the right track, and these are signals that are measurable, that are observable. But this is still, in order to start building an actual robust model that you can use for this real-time dynamical inference, there's a lot of complexity that you now have to start to consider. So, we have this system in which your brain is talking to your spine, is talking to your peripheral nervous system, is it, giving those signals to the muscles, and there's complicated feedback loops at each of those sets. But I also just want to sort of lay out all of the complexity that we're dealing with here, which I think is a large reason why people haven't, done too much with this problem before. So, first, as I've mentioned, humans are overactuated. They have a lot of these muscles that are performing very similar functions. And so they're happening, those forces are occurring synergistically or antagonistically in order to maintain stability. There's also all sorts of crazy continuum contact forces to account for. There's geometric complexity even with just a single muscle. So I've been drawing these as this nice, single line of action, but that's a curve in 3-dimensional space. That's dependent on the configuration of your arm at any point in time. The pennation angle, or the angle of fibers in the muscle, can affect that force exertion. The tendons that attach to the muscles aren't just point to point; they're often fat, turning into sort of aponeuroses. There's also mechanical complexity within that muscle. So, you've heard of fast twitch and slow twitch muscle fibers. They have hysteresis, depending on whether they're concentric or eccentrically contracting. That changes things. As far as I can understand, nobody understands anything about fatigue in terms of this kind of modeling. And this is all just not even considering the neurological complexity of, the way that the neurological system actually makes a muscle activate isn't per muscle, it's per, quote, motor unit. And there can be tens to hundreds of motor units in a given muscle. There's these ideas of tetanic and subtetanic contractions, feedback versus feed forward elements of this control. All of it's incredibly complex. And so just to give you an idea, I colored these different levels of complexity with green is, I think if we tried really, really, really hard, we could maybe measure it. And red is, I have no idea at all how to measure this. And so there's really a lot of complexity that's just going to go unmodeled, I think, no matter how sophisticated we make these systems. And so, one of the challenges that I've encountered with this work is the more closely we attempt to, add in these biological mechanisms to our models, the more we have to start, relying on these values and parameters that, exist sometimes in literature, like, how stretchy is this tendon, or things like that. But if you actually look at where these values come from, it's, they stretched a cat tendon 30 years ago, or this was from a cadaver study of 3 people and they all had 3 different, moment arms for this particular muscle. And so it's really not clear how much of these values we should even trust. And so for my work, I'm trying to come at it a little bit differently and say, okay, we're not going to tie ourselves to one particular model. Instead, I want to build up a suite of possible models, which range from sort of the full black box neural network models all the way to white box models that maybe do account for these actual mechanisms, and to do this in a way that's quantifiable and it's principled. Which, as a side note, if we do manage to come up with a good model that uses these literature values, that can serve as sort of a validation of those literature values. Okay, so this is sort of the current status of the work. I'm now working to start building this suite of models and evaluate our existing this existing body of data that I've spent all this time building up. Actually evaluate these models on those data sets. And so I'm going to show you one possible suite of models that I'm currently working to implement. This is kind of the mathiest this talk is going to get, so don't panic. I'll walk you through it. But basically, I'm looking at the inference problem in which, okay, what we have as our output to the model is this joint torque at the elbow, and as inputs, we have some sort of deformation value of the biceps that we get to define. And we have the kinematic configuration of the individual. As I said, I'm not really interested in trying to infer those kinematics too. There are plenty of other sensors that I think can do a better job. The power of this research is really in ultimately trying to figure out the actual biceps force. But the whole reason we're doing this research is because we don't actually have a ground truth measurement for that. So really what we're evaluating against for now is that joint force. So we can think about sort of a model-free baseline for this kind of a model, where that output torque is just some general function of this deformation value, which could be it could be this contour as I parameterized it here. It could also just be pixel values, and I'm looking at that as well, and have this be some sort of big neural network or big nonlinear function of these two values. But then we can start imposing different levels of structure in a principled way. So we can say, okay, maybe that mapping from this deformation value to the biceps to the biceps output force is still this general unknown nonlinear function. But we do know that this is occurring in the context of all of these other elbow flexors and elbow extensors. And so we can take from literature some sort of distribution model over what those different muscles are probably doing for this particular motion. And I've started to highlight, you'll see in orange, things that we're starting to have to assume based on this model. So that's one assumption, but it might make our model more generalizable. And similarly, you could, instead of having it be just some sort of constant function, say the biceps is always some constant percentage of that output force. We could say, okay, depending on, basically this is geometrically, we can look at how that muscle geometry is changing based on the kinematics, and then just add that to models of the other relevant muscle groups. But in that case, you start having to assume things like attachment points on that muscle or on the skeleton. Okay, that's adding in the multi-muscle dynamics part of it. Then we can look at the individual muscle tendon unit dynamics, and we can say that again, okay, the length of the muscle itself is a function of the of this deformation of these kinematics. It can be whatever we want. But tendon dynamics in some cases are pretty well known. These stiffness values and things like that, they're a lot easier to measure. And so we can input those stiffness values that we know. And actually, similarly, from our models, if we have these full three-dimensional values, even if we're just looking at a single cross-section here, we have these full three-dimensional data sets, we can go back and look and see if this length that we're assuming is consistent with that length from our three-dimensional scan. And so lastly, we can actually impose a more specific ellipsoidal dynamic to that individual muscle and say that we're assuming that muscle is isovolumetric, and this is the way that the length should evolve based on that ellipsoidal assumption. So that's kind of one possible suite of models that I'm looking at to see if we can then start inferring this output force. Here, as I said, just for this this output joint force, but ultimately for individual muscles as well. So with respect to validating these models externally. I'm also looking at a couple of different directions there. As I've said, I think several times, the power of this research is that we don't have a direct, non-invasive, in vivo way to measure these muscle forces, at least in humans. We can't cut open humans, live, healthy humans anyway. So we have, I'm looking at a couple of different directions, possibly future collaborations to start, as a way of at least seeing if the force values that we're getting are consistent with other sensors as well. So one option is to do an animal study with a more wet lab oriented group, and put some of these buccal force tendon sensors on an animal tendon, and see if the values that we're getting are consistent. But we're also looking at just a couple of other sensors for consistency. So looking at acoustic myography for, as muscles exert force, they actually also vibrate. I may talk a little bit about that later, depending on time. Looking at a technology called Cine-Dense MRI, which is, it looks at sort of displacement over time within a given scan. And also a method used by Daryl Thalen's group, in which you can tap a tendon and use that as a measure of the loading on that tendon. Okay, so I don't have too much time left, so I think I'll just close out and not pause for questions here. But I want to end with kind of a couple of proof of concept applications that I'm thinking about in a couple of different domains. So first, just recall that we do have this work on measuring these contours over time in an automated way using this optical flow method. And so this is kind of the image of the control signal that I want you to have in your head as you see these different applications. So first of all, one interesting avenue that this opens up is a different way to control the output force of a given device. So just for simplicity, in this case, think about a teleoperation case in which you have sort of an anthropomorphic robot that you want to exactly mimic the motion of the human user. Ultimately, I want to also think about strapping these devices to people, but that opens up a whole other can of worms. So just as a sort of simple example, let's think about a robot in which we're interested in controlling simultaneously both the kinematics of the robot and the force. And this is going to be a very non-standard control setup, but it's something new that we could start thinking about based on these sensors. So so in this case, we have some sort of controller for this robot with you can maybe control the kinematics directly using some sort of goniometer or motion capture. But if you want to control forces, the way that's done today most of the time is you take that activation signal that I've mentioned using electromyography, and you usually take a differential signal across kind of the agonist, antagonist, biceps, triceps. You take a difference of that, and that feeds your feed forward force control. The problem with that is that that's really not a measure of force. That's more of a measure of the impedance across that joint. And so one thing that we can think about doing with this deformation measure is, instead of having this be our force signal, have the deformation be the force signal, and then potentially have this activation signal be a modulate the stiffness parameters of that controller. And potentially, this could make these movements in which we need to be really impedance matched to our subject, possible or easier. And one example sort of case study that I've been thinking about is something like catching a ball. But this is also true for, for example, collaborative manipulation tasks between, a human and a robot and things like that. Okay, so a second set of applications that I want to touch on that's maybe a little bit less known in this community is advancing the state of the art in these musculoskeletal modeling frameworks. So the way that most people do this force inference these days is using systems, if you've heard of OpenSim or Anybody, things like that, where you feed your system some sort of joint velocities and angles, maybe from motion capture, and then you perform inverse dynamics, and that gives you your joint torques. And then they have some sort of an internal cost function that says, okay, based on these joint torques and what we're seeing from these EMG signals, we think these are the muscle output forces. And one of the things that direct force measurement allows you to do is, okay, maybe we can't measure all of the muscles, but we can at least measure one and see if these cost functions are consistent. And that can sort of tell us, okay, for final applications, which of these cost functions are useful and which are not, are actually true and representative. And then secondly, once we do start to be able to measure a bunch of these forces at the same time, that can start to enable actually forward dynamic control, which really is not at all used because it's so messy right now. Even getting just a forward dynamic simulation of a human arm to stay still is beyond a lot of controllers. Okay, and lastly, I just want to mention sort of more of a future direction for this research, but a reason that I think it's kind of powerful is that I've shown this picture before of how human muscular dynamics happen, and somewhat surprisingly, we have measurements that we can measure at different places along this musculoskeletal or neuromuscular control loop. We can measure the brain in a limited way, but we can measure the brain via EEG, ECOG. We can measure along the spine or along various pieces of the peripheral nervous system with these nerve cuffs, and we can use EMG to measure that final activation that goes into the muscle. But the thing that we really don't have is a measure of that final output force. So, in some ways, looking at these mechanical signals really closes the loop here and can allow you to potentially, have better understanding of what we're seeing from these other signals, potentially looking at, simultaneous EMG and muscle dynamics can actually give you, a better understanding of that relationship between activation and actual force output. And secondly, there are all sorts of different pathologies that show up at different places in this whole loop. So, for example, cerebral palsy is a brain condition, but it causes these very specific physiological physical changes in the musculature in terms of like muscle stiffness and things like that. And so, really, in order to understand that full loop, we really want to be able to measure at multiple points. And so hopefully this can ultimately lead to new insights, not just for novel device control schemes, but also for in the space of healthcare and rehabilitation, and really understanding these pathologies. Okay, perfect. I've got 2 minutes. So I'm now going to close with just a quick I'm going to touch on one additional sensor that we've looked at that showed up before, but in addition to deforming during muscle force output, muscles also vibrate, which is kind of wild. But they vibrate in a known way, and we can measure that vibration using something called acoustic myography. And we've done a little bit of work in also using this signal to measure output force. And we do have some preliminary data that shows that the particular values of this acoustic signal, so this multiplying, this amplitude frequency product is in fact correlated with this output force. And we're now trying to make these models better and also use this potentially for control as well. All right, so I will close with just kind of summing up what I presented today in terms of things that I actually do consider major contributions of this work. So first, I showed a couple of not completely novel data sets studying a phenomenon that, as far as I know, very few people have ever studied. That we, and put these data sets online for not just for the biomechanics community or the robotics community, but for farther afield people like animation community as well. And then second, I presented a suite of possible models for showing this relationship, or for quantifying this relationship between deformation and force output. And third, a couple of proof of concept applications that kind of show where this research can go and where I hope to continue pushing this research throughout my academic career. So with that, I'd like to thank my wonderful advisor, Rujana, the rest of my committee, and the many other researchers who helped on this work, many of whom are actually undergraduates that have worked with me. So I encourage you all to work with undergrads. They're great. And I'd also like to thank our sponsors. And with that, I will open it up to questions.
Thanks, Laura. That was a really excellent and super interesting talk. And so I'm going to start with the first question from the audience, especially as our other panelists turn the cameras on. From Wei-Shi, the approach in this talk seems to focus on the macro force displacement in relation to a whole muscle. Do you have some ideas on how this ties to micromechanical relations? For example, like how sarcomes or myofiber changes when force is applied?
Oh, that's super interesting. Yeah, I think so. Longer term, I think it would be really cool to have, multiple, because I will say I chose the there are different levels of abstraction that you could choose to look at for this work. That is very true. Like I have sort of lied to you in the fact that I said, I am looking at this one muscle, whereas, even the biceps, technically it has like 2 different heads and 2 different attachment points up near the top, and 2 attachment points at the bottom. And so, we have to make choices here. And I think, individual muscles is one abstraction that I chose to kind of be expressive enough to start talking about these crazy motions that humans can do in terms of you have not just one muscle group per joint or anything like that, but is also not so detailed that you can never get anywhere on the full body system. But I think ultimately, in order to really, like, the ultimate scientific goal with a lot of this work is trying to, can we, now that we have this gross measure of muscle force, use that to back out, okay, what is the underlying chemical system doing? What is these, these individual sarcomeres, what are they doing? And I think based on the sensors that I've had, I haven't looked into that all that much, but I think depending on, I think what it will take is kind of a, advances in sensing technology. I started this project thinking that I was going to be mostly a control theorist, and I've spent most of my graduate work doing a lot of imaging and segmentation and sensing and trying to leverage sensors in new ways. And so I think in order to, my understanding is that most of the work on sort of the micro scale dynamics of muscles is done in a wet lab with, cadaver pieces or with, frog legs and things like that. And inherently, when you take something out of the body, it's going to change its behavior. And so I'm really interested in that question of, can we start measuring things in vivo at that scale? Sorry, that was a long-winded answer.
So one of our other panelists can ask a question.
Sure, I can ask a question. So it sounds like because your approach is very novel towards understanding how force is a function of deformation of the muscles, that you've spent significant time collecting data. So now, knowing what you know, how would you further expand the current data set that you have, knowing after having collected what you have, what's actually useful and what is more redundant?
That's a great question. So I think, and I think I will have a better answer for you as I start wrapping up this actual modeling work. So I presented you that big suite of models, and then I didn't give you any results on which models worked best because that's still in process. But I think my hope is that, we have this initial big 3D static data set. And there's a lot of ways in which that data set is limited, right? It's only static, it's not occurring. There's going to be some, velocity related changes in how these dynamics evolve, but hopefully what that can show me is, I think the biggest insight I hope for from those big 3D data sets is some level of spatial localization. Say, okay, based on this, the cross section that's actually giving us the most information about this muscle output force is, at this particular location along the arm. And then for that particular location, we can start taking scans that then under a wider variety of conditions and for a wider variety of subjects. And so we've sort of in parallel started this work on, okay, given that we're ultimately going to get a single cross section, we want to be able to track that cross section. And so we've started this work on sort of optical flow and that, so that we can start using it as a control signal even before we have those insights. But that's kind of my hope going forward, is that each new data set then kind of shows us the next step for what we should be looking at and refining next.
Kind of along those lines, I think something that was really compelling that I saw was like trying to understand like hand manipulation. Like that video was like super cool. Do you think a cross section is like enough to understand all the small like little muscles in the hand, or is it, do you think we're gonna need like other signals?
Yeah, so I mean, a lot of the muscles in your dealing with hand motion, a lot of those muscles are actually up here in your forearm. And it would be nice. So I think there's a lot of really interesting questions as far as, I think the reason that I landed on muscle deformation is because unlike EMG, where you just put an electrode on your skin, you can, and probably I should have talked about this, but like you don't know exactly where that electrical signal is coming from. It's like sort of all the surrounding muscles. It's this little patch of, there's no way to understand exactly what different muscles that signal corresponds to. The nice thing about this sort of ultrasound measured deformation is that, we still need to show that particular muscle is correlated with that particular muscle's output force, but you can at least look at an individual muscle and say, this is the deformation that's happening for that muscle. And so for something like, we're kind of limited in terms of, we have one ultrasound probe right now, but ultimately, if you were able to measure multiple muscles simultaneously, that could start giving you the difference between, say, me just holding my hand in space and me, clenching my elbow really tight so that it's really stiff. And if you were to come up and poke it, you couldn't poke it anymore. Those are completely, no kinematic system is able to tell you that. And then for things like the hand, it would be really nice if there was, one muscle that mapped to one finger. But if you've ever looked at like the anatomy of the human hand, that is not at all how it works. The hand is both over and under actuated, and it's all tendon driven. And so I think there's a lot of interesting questions there about, which muscles would you really need to measure in order to make, really understand the particular forces and torques that you're interested in. And, beyond that, okay, now you have an anthropomorphic robot hand that you want to control. Does a one-to-one mapping make sense? Or are there, other control tricks that you can play and things like that? I find all those questions really interesting. I think we've stuck to the elbow mostly because it's a comparatively simple joint. It only has, 4 different redundant muscles instead of, 24. But, there's still complexities even there. And, the fact, if you just, I spent a lot of time just looking at my hand, like turning it over, this whole like forearm joint, is that at your wrist? No, it's really your whole forearm doing your whole radius moving relative to your ulna. Like, there's a huge amount of complexity, which I think is one of the reasons no one has touched this problem with a 10-foot pole, is because I think roboticists like to think, oh, someone else will solve this problem for us before we actually start strapping devices to humans. But it turns out the biomechanists don't know how to do it either. So yeah, that's what I'm working towards.
Hi, I have a very practical question about the ultrasound measurement that, is the only way to gather the ultrasound measurement for someone to be there, like with this, like wanding you with the ultrasound wand, or can you gather that same data in, I was thinking towards your applications slide that, if you're having a human teleoperating, you don't really want another human there with the ultrasound wand, maybe.
Yeah, so I think it depends on the, we're using the device that we have, but there's a lot of research in, other domains happening into like portable ultrasound. Right now, the form factors are not, ultimately, if I'm going to be controlling a device, you want it to look more like, for example, a cuff or something like that. And, that's a whole other area of research. I believe some people are working on it. There are some ultrasound cuffs out there. But there's also just more portable technology happening in terms of, there's a probe called, I think, like the Butterfly or something, that's attached to your phone that, you don't have the big box, you just have, so like there is a lot of research in, making these devices more portable. And certainly in terms of strapping, strapping that device to someone, you'd ultimately not want it to be a human operator. There's a lot of work out of like Johns Hopkins as far as like automated scanning of people. So, another direction for the lab setting would be to have, a robot doing, perfect impedance matching along your arm do those scans, if we wanted something really detailed.
I want to be mindful of time, but thank you so much for coming to speak to us. And thank you again for a really excellent talk at this GRASP SFI seminar. So yeah, you can hopefully contact Laura through her page. And thank you so much, guys. Have a great rest of your afternoon.
Awesome. Thank you so much.